Oh, sorry for this. Okay, I forgot to record this session. But the 1 hour is almost there. But let me recall over quickly. I forgot to record this. Sorry for that. Yeah. So what is the thing? Whatever I have done till now. So let me summarize this thing. Given field Q of rational numbers. So this field is that like x to the power. Okay. So the problem is that we need to find the splitting field of this polynomial x to the power n minus 1. So basically we want to study cyclotomic extension. So what is the cyclotomic polynomial? I will explain you, but this is the polynomial which gives us all nth root of unity, basically x to the power n minus 1. We want to study its splitting field basically. So yeah, this is the thing. Okay. So given the field of rational numbers, this is the polynomial. What is the splitting field of this polynomial? This is the natural question to us. And what is the degree of the extension of the splitting field of this polynomial? So basically, this is the question to us. Okay. So what is the answer to that? In order to find the answer to that, we are trying. First, the observation we see here is that this polynomial x to the power n minus 1 is not irreducible, except the case n equals to 1. n equals to 1 के केस में तो just linear polynomial है. It is just a linear polynomial, so it will be irreducible. But for n equals to 2 and onwards, it is not irreducible. We proved that. How we proved? We proved that this x to the power n minus 1 can be written as x minus 1 plus into 1 plus x square up to x to the power n minus 1. We have to write it. Right? This is not infinite sum. We have to write it here. Thus, x to the power n minus 1, right? So that means x to the power n minus 1 is not irreducible for n greater than equals to, right? So now this polynomial fx equals to x to the power n minus 1 qx. So let's denote this set of its roots by the group mu n. You will see that this forms a group, even cyclic group, cyclic abelian group. So mu n equals to z belongs to complex all complex numbers, so that this power nth power is 1 basically. So this is z to the power I equals this form, polar form, we can write this number 1. So then we see that these are of the form 2 pi I k pi I by n, where 0 is less than n equals k is less than n. From n onwards, this repetition will start. So only up to 0 to n, basically all a n degree polynomial can have at most n roots in complex, exactly n roots, right? So now we prove that this mu n forms a group. Basically, how we prove alpha and beta in mu n? So alpha beta is also in mu n. So how we did this? Alpha to the power n is 1, beta to the power n is 1. So that means their product should be also there. Also alpha beta to the power n is also alpha beta to the power n is basically alpha to the power n, beta to the power n. So similarly, associativity is obvious. Identity is also there, and the inverse is also there. So this is group. Even this is cyclic group. This one zeta is equals to e to the power 2 pi by n. E to the power 2 pi by n. This is a zeta. Suppose this is the generator of this cyclic group. Any element can be written as its power, basically 0 to n minus 1. Yeah. So yeah, any element can be written as its power, and we prove that this group is isomorphic to the Z mod nz group by this given isomorphism. So we have this group of all nth root of unity, which is a cyclic abelian group. Cyclic implies abelian, yeah, cyclic group. The group of nth root of unity isomorphic to Z mod nz. Then Z mod nz has phi n generator elements co-prime to n. So that means mu n has a phi n generator, which are zeta n to the power k, where k is co-prime to n. So now we prove the you can say it is lemma or observation, something like that. So t divides n if and only if mu d contains in mu n. So one side is fine. So if mu d is contained in mu n, so both are group. So that means mu d is subgroup of mu n. So by Lagrange theorem, order of subgroup divide order of group. So d divides n. So that is fine. So the forward implication is that, so if d divides n, we have to prove that mu d is contained in mu n, right? So how will prove this? How will prove this? Mu d is contained in mu n. We have to prove this. Okay. So how will do this? X belongs to mu d. That means x to the power d is equals to 1. So d divides n. We have to prove that mu d is contained in mu n. So we choose any element of mu d and we have to show that this element is also in mu n, right? So if we choose any element x in mu d, that means x to the power d is 1. So we have to prove that x to the power n is also 1. So x to the power n, to show x to the power, so since d divides n, how we can write n is some multiple of d, basically rd. Okay, so what is this meaning? X to the power n is equals to 1. If and only x to the power rd1, we can write n as rd. But rd, how we can write? X to the power d to the power r. But x to the power d is 1, so its rth power is also 1, basically. 1 to the power r is 1. So yeah, x will be mu n. So we are done. So after this, we here we prove that d divides n if and only mu d is contained in mu n. So after this, we see that a definition, what are the primitive nth root of unity. So basically the generator of the group cyclic group mu n are called the primitive nth root of unity. So these are all element k, these are all element zeta into the power k, zeta into the power k, where k is coprime to n. So these are all primitive nth root of unity. Now after this, we see here geometric interpretation. Let me write here geometric interpretation. Okay, so here is the geometric interpretation. This is the geometric interpretation. Geometric interpretation. Okay, so what is the geometric interpretation? First root of okay, so here is the thing, right? What is, where is the highlighter? I guess there should be some highlighter as well. Yeah, this, maybe this is the highlighter. So see, this is the okay, this is the first root of unity. Okay, this one is to select, but there should be some highlighter as well, right? This is eraser, this is highlighter. Yeah, this is the highlighter. Okay, so yeah, see, this is the first root of unity, and then this one and this one is the second root of unity, elements of mu2. Then this one, this one, this one, and this one are third root of unity, and this one, 1 minus 1 iota minus iota, these are fourth root of unity. So we see in complex plane they form a regular and polygon, sides of regular and polygon, these points basically. So this, there are two observations from this geometric interpretation. This means points of mu n are unimodulus equidistant points in complex plane, and elements of mu n forms regular n-sided polygon in complex plane. Now see, when n tend to infinity, what happens? There are infinitely many points. These points are all in circle, basically infinitely many points, right? In circle, equidistant points in circle, like. So phi n(x) is nth cyclotomic polynomial. So we define after that this nth cyclotomic polynomial. So how we define this nth cyclotomic polynomial? This is the product of all nth primitive root of unity, basically. All primitive root of uh, all nth primitive root of unity, which are generators of mu n, basically. So yeah, these are all generators of mu n. The product zeta belongs to mu n. Zeta is primitive x minus zeta. So this is the thing. Okay. So after this, we see some cases like what is phi 1x, what is phi 2x, what is phi 3x, phi 4x, phi 5x, so on, so on. And then x to the power n minus 1 is, you can write product zeta belongs to mu n x minus zeta, x minus 1. Okay, fine. Okay, then what? Then for n equals to 2, x square minus 1, x minus 1, x like n equals to 1, x minus 1 is basically phi 1x. N equals to 2, x square minus 1 is basically x minus 1, x plus 1, which is phi 1 and phi 2 product. The observation here from is that x to the power n minus 1 is a product of phi dx, where d is divisor of n. This is happening in 1, 2, 3, 4 all cases. So we prove this observation, then x to the power, this is just easy proof, right? X to the power n minus 1 can be written as a product of linear factor, basically all its roots factor. So then you can, any element zeta is mu n, it has suppose some order d, then d divides n, order of element divide order of group. So d divides n, and if an element have order d, then zeta belongs to mu d, and zeta is primitive, dth root of unity. So but what is this term? What is, okay, here is this highlighter. So what is this? This highlighter is not good. Zeta belongs to This one I have to use pen. Where is my pen? This is the pen. Zeta belongs to mu d. Okay, zeta belongs to mu d. So this is basically okay. So this means this is a deep cyclotron product of our zeta belongs to mu d, zeta primitive, and x minus zeta. So this is phi dx. So x minus 1 can be x to the power n minus 1 can be written as product d divided by phi dx, and this cyclotron polynomial. Then we do for simple case, like for when n is prime, so x to the power p minus 1 can be phi 1x and phi px, and we see this is the phi px, and then we show that this phi px is reducible. So that means one is root of either of one. See the zeta, the generator of mu p is one element of either phi 1x or phi px, but it cannot be element of phi 1x. Basically phi 1x has only one root, right? So this is one only, but one is not the generator of phi px. So this must be root of this polynomial gx. So we prove that gx is irreducible, and zeta is a root of gx basically, since zeta is the root of x to the power p minus 1, but zeta is not the root of phi 1x. So zeta must be root of gx, which is phi px. So zeta is the root of phi px. So and then we prove that gx is irreducible. Then if we prove gx is irreducible, this is monic, then this is minimal polynomial for zeta. So degree of extension field q zeta is exactly the degree of this polynomial gx in that case, and the gx is phi px basically, p cyclotron polynomial. And then if we prove this is irreducible, then this is the minimal polynomial, then this its degree is the degree of extension field q zeta, and q zeta is a splitting field since it contains zeta, so it contains all other roots. Basically all other roots are just its power, so it is generator of the group all of the roots of this polynomial x to the power n minus 1, p minus 1. So we are done in that case. Only need to prove that this is irreducible. So how do we prove gx is irreducible over any field if gx plus 1 is irreducible over that field? So gx plus 1 is this polynomial, then we write this by extent, then we use Eisenstein criteria and prove gx plus 1 is irreducible here. So gx, if gx plus 1 is irreducible, this implies gx is irreducible. So gx is irreducible monic minimal polynomial which has zeta p as a root. So q zeta p over q degree. Okay. 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 So the extension of q zeta p over q is degree of gx, which is basically phi px. So this degree phi px has degree Euler phi function phi p, so which is p minus 1. So yeah, so we are done. So then we want to prove this for general number n. So what we did, phi n x is a monic polynomial in zx of degree phi. So we want to prove this, right? This statement we already didn't prove till now, but this is the summarization what we did up to now. So sorry, I forgot to record, but yeah. So phi n x is a monic polynomial. I hope the recording is now going on. I couldn't see anything in my screen, but let's check. Let me check. Recording हो रहा है नहीं हो रहा पता कैसे चलेगा? Recording in progress. Okay, fine. So let's go there. So phi n x is monic polynomial in zx of degree phi n. Basically monic is fine. This is product of x minus zeta. Zeta is primitive, so basically x to the power n will number of x to the power, like how many primitive root of that much power will come, and coefficient will be 1. So this is monic, and the degree is basically phi n, Euler Poisson function phi. So how will you prove this? So how many primitive nth root of unity? These are precisely zeta into the power k, where k is co-prime to n. These are precisely k belongs to z plus, and GCD of k comma n is 1 less than k comma n, and k less than n. We have to write here k less than n. Where is this pointer? K less than n. Yeah. This is the thing. So this is basically phi n. So this degree is phi n. So now only thing to prove, where is this? क्या हो रहा है? Yeah. Yeah. So the only thing is now to do is that this thing. Only thing to do this is in ZX basically. So how we will do this? Okay. So how we will do this? How we will do this? Okay. So how you can write x to the power n minus 1? Where is this point? Yeah. X phi d x, right? So how you can write this? This you can write. How you can write this? Okay. The only thing phi n x belongs to zx. For n equals to 1, it is fine, right? Okay. Let's do this by induction. Right? For n is equals to 1, x minus 1 belongs to zx, right? Use induction here. Suppose true for all d strictly less than n. To prove for n case. So how you can write this? To prove phi n x belongs to zx. Okay. So let's write this given notation. Fx is equals to, let fx is equals to product over all d, d divides n, d strictly less than n, not equal phi d x. So this is the notation. Now see, for all d less than n, this is true that phi d x belongs to zx basically. So this is, so that means this fx belongs to zx by induction hypothesis. So what is then? Then you can write x to the power n minus 1 is equals to fx dot phi nx. Now see, this means what is this meaning? This means fx divide x to the power n minus 1 in the where the phi x belongs. So phi x will belong to at least in a splitting field. Okay. In zeta n basically. So what is this meaning? But fx belongs to q x and x to the power n minus 1 belong to qx. So by division algorithm, phi n x, yeah, this is the division algorithm. Yeah. Phi in x is also in qx. Now phi n x is in qs, but by Gauss lemma should be also in zx, right? Since this fx is in zx and x to the power n minus 1 is zx, so their product is also zx. By Gauss lemma implies phi n x zx. So yeah, we are done. We proved that this phi n x is n cyclotomic polynomial is monic polynomial with integer coefficients of degree phi n, basically Euler phi function phi. So what next? If we prove that this is monic polynomial of degree phi n with integer coefficient, we only need to show this is irreducible polynomial. If we prove this is irreducible, then it is minimal polynomial containing zeta as a root, right? Why zeta is its root? The first question should be that, right? Why zeta is its root? See here, where I write. Okay, where I write this thing. X to the power n minus 1 is equals to product d divides n phi dx at each cyclotomic polynomial. Now zeta is root of this one and left hand side. So at least one of the polynomial on right hand side this has a root. Now see, if d less than n and phi d has zeta as a root, then zeta belongs to this mu d basically, since zeta is root of phi d. So that means phi d का अगर एलिमेंट है तो वो बेसिकली किसका रूट है? x टू द पावर d माइनस 1 का रूट है. बट जीटा तो हमने बोला था कि प्रिमिटिव nth रूट ऑफ यूनिटी है, तो जीटा कैन नॉट बी इन यू डी, राइट? d लेस देन n. सो जीटा शुड बी रूट ऑफ phi n x, राइट? सो जीटा का ओनली चॉइस ऑफ रूट phi n x ही है बेसिकली. सो जीटा phi n x का ही रूट होगा nth साइक्लोटोमिक पॉलिनोमियल. So अगर हम proof, if we can prove that this phi n x is irreducible, we already proved this is monic of degree phi n, Euler phi function phi n, and with integer coefficient. If we can prove this is irreducible, then this is a minimal polynomial containing zeta as a root. So the polynomial containing zeta will be the splitting field for this polynomial, and its degree will be exactly the degree of the minimal polynomial, which is phi n basically. So degree of extension will be phi n in that case. And so the degree of splitting field of this x to the power n minus 1 will be phi n in that case. So we only need to show this polynomial is irreducible, but that is not easy task to prove. So let's do this. This is the harder part to show. Theorem. The cyclotomic polynomial phi n x is an irreducible monic polynomial in zx of degree phi. Irreducible monic polynomial in zx of degree phi of n. Right, this is the thing. How will prove this? How will prove this? Degree phi n is fine, in zx is fine, monic is fine. Only need to show is irreducible. Only need to show is irreducible. If not, then what happens? If it is not irreducible, you can write is a product of two factors, right? So you can write phi n x as fx gx. Without loss of generality, assume that fx is irreducible. Like see, zeta is root of this phi n x, right? Nth primitive root of unity. Then either zeta is root of fx or zeta is root of gx basically. So which of the factor have zeta as a root? Reduce that factor to irreducible factor, right? So suppose without loss of generality can assume zeta is root of fx and fx is irreducible. Okay, zeta is root of fx and fx is irreducible. So what? So what? So if zeta is root of fx, then zeta to the power p, since zeta for, so what, for any time p not dividing n, what we can do, zeta p is also root of phi x, right? So what is the meaning of this? Implies zeta p is either root of fx or gx. If it is root of gx, then what? If it is root of gx, then what? That means g zeta to the power p is equals to 0, right? That means what is the meaning of this? G x to the power p has zeta as a root, right? Right? Right. G x to the power p has zeta as a root, but we assume that zeta is a root of fx and fx is irreducible. So that means fx is a minimal polynomial, right? Here, what you can write is x minimal polynomial. कहाँ गया? ये pointer मेरे भी zeta. Okay, fx is minimal polynomial of zeta. So what? So what? So what? So this means that fx divide g x to the power p, right? Fx divide gxp in zx, right? Both are in polynomial in zx. So what is the meaning of this? This implies g x to the power p can be written as fx dot hx for some hx in zx, right? What is the meaning of this? Okay, going to mod p, taking mod p gx p is equals to, let's denote mod by f bar x h bar x, right, in this way. So but see, in the finite field, every element a to the power p is a, basically fp. So in fp, so yeah, so what you can do, this you can write as the g bar x to the power p is equals to f bar x h bar x. What is the meaning of this? This means f bar x divides g bar x to the power p in finite field fpx, right? So since fp is a field, so fpx is a pid. fpx is a pid, right? So fpx is a pid and fx is irreducible polynomial. So fx is a irreducible polynomial, so fx divides gx to the power p. So a irreducible element is a prime element in PID. So p divides some element, then p divides either a or b. So p divides. So from here you can conclude that since fx is irreducible implies prime, so fx f bar x divides g bar x, basically. So this implies what this implies. Okay, let's see. Where is this? Bar x is equals to this thing, right? So f bar x is equals to this thing. Okay. F bar x divides g bar x to the power p. So f bar x divides g bar x. So what? But see, g bar x has a zeta as a root as well, right? That means this means there is the point g bar x has at least one common factor x minus zeta, right? Right. So what? So now reducing the mod p this polynomial phi n x. How we write this phi n x? We assume that this phi n x is reducible in that case. So reducing mod p phi n x is equals to phi n x bar is equals to f bar x dot g bar x. So see, this has multiple roots. This implies px since f bar x and g bar x has common factors. This implies phi n bar x is not separated in f over fpx, but it is separated, right? Phi n bar x is, but it is separated. How it is separated? This is contradiction, right? Contradiction. How? Phi n x is basically collection of some roots of this polynomial x to the power n minus 1, right? And we prove in last lecture, I guess, that this is separate. Let's do it again. And p is co-prime to n. This x to the power n minus 1 is separated for p all fields of characteristic say p not dividing n. How you will prove this? This is fx. What is f prime x? This is nx to the power n minus 1 has 0, has root only at 0 for p not dividing, and fx is not equals to 0 at x is equals to 0. This implies fx has all distinct roots in fpx where p comma n is equals to 1 This implies phi nx has all distinct roots in fp fpx. So yeah, so this is the done. So what is the contradiction from here? That phi x is not separate, which is a contradiction. So yeah, we prove that this implies our initial assumption is wrong, that zeta is the root of zeta cannot be root of gx. Sorry, zeta to the power p. This implies zeta to the power p is root of fx for all p coprime to n. P prime coprime to n, right? P prime coprime to n, these are all roots, right? And these are all is a root of fx. We prove this one. Now for any a, we have to prove that zeta to the power a is a root of fx, right? We have to prove that zeta to the power a is root of, okay, all generators are there, we need to prove, right? So how we will prove? We need to prove that all coprime generator, okay, okay. Since now for any, it is a, for any integer a coprime to n, what we can do, we can write a is equals to p1 p2 pk pi prime and coprime to n, prime and gcd of pi comma n is equals to 1, right? So pi prime, pi prime, yeah, okay. That means from hereward, that means zeta to the power p1 is pi is root of fx from above observation, from above part we proved there. That means this is a root of fx, that means zeta to the, this is root of fx, right? Then this to the power pj is also root of fx. This implies carrying in similar way, we can write zeta to the power a is also root of fx. So done. We prove that any element a relatively prime to n is root of fx. So every generator is there. Yeah. So this implies every primitive nth root of unity is a root of fx. That means fx is equals to phi nx, since we assume that fx is irreducible, showing that phi nx, this implies. So yeah, we are done. Irreducible. So yeah, we are done. So what is the consequence of this? The consequence of this is thus phi nx is minimal polynomial for zeta n. So this implies degree of extension q zeta n over q is equals to degree of phi nx, but we proved that this degree is exactly phi n, so its degree is exactly phi n. So yeah, and any field containing zeta n will contain zeta n square, zeta n cube, so on, so on, so on. So this means that This means that q zeta, thus q zeta n is the splitting field of x to the power n minus 1, and degree of extension is fine. Yeah, so I answered the problem which I asked initially, right? I asked that what is the splitting field of the given polynomial x to the power n minus 1, and what is the degree of extension. So this is the degree of extension and this is the splitting field. I give you everything explicit construction. So yeah, so this is the thing I want to cover up today. Some of students asked me these things. So yeah. So, oh, bet. Give me a minute. Okay, so this is the thing. So we proved this cyclotomic extension theory part. So let's do some examples of this. We already did a lot of examples related to this, but let's do an example. So what is the example? Find degree of extension of splitting field पहला x to the power 8 minus 1, दूसरा what you can say cos 2 pi by 10 plus I sin 2 pi by 10. दूसरा this element, yeah, you can write x to the power 10 minus 1 for this. This is the root of this. So you can write x to the power 10 minus 1. System. Second one is yeah. So we have to do this. So what is the degree of extension of the splitting field of this polynomial is equals to phi a. What is phi a? A dot 1 minus 2 cube, right? 1 minus 1 by 2. What is this? 4. What is this? Phi 10, which is 10 dot 1 minus 1 by 2, 1 minus 1 by 5. Which is this? 10 dot 1 by 2 dot 4 by 5. What is this? 4. Yeah. So these are the examples. So let's do your practice assignments. Okay. I completed already all practice assignment, first, second, third, fourth, fifth, sixth, seventh, eighth, all week. So let's do your previous year assignments. Let me open that. Where is that? Give me a second. This is the NPTEL course. Let's do your assignments. Okay, previous year assignments. Okay. So this is the question. Choose all correct statement. Q and C the field. Q and C the field of rational and complex numbers respectively. K, F are field extension of Q. Phi mapping K to F is a field homomorphism. Phi R equals to R for every R belongs to Q. This is the first question. So let's do this. I'm not sharing my screen. Oh. Oh. Am I not sharing my screen? What the mess up going on? Oh god. Okay, whatever. So let's do this. So now do your previous year. We will do your previous year assignment. Okay. Question. Choose all correct statements. So first question is that Q denote field of rational numbers. C denote field of complex numbers. Q denote field of rational numbers. C denote field of complex numbers. So what we want to do is that what the first option is that phi mapping. What is the first part of this question? Let me see. K to K and phi mapping K to F is any field homomorphism and where Q comma F is a Q comma F is a field extension of Q, then phi R equals to R for every R belongs to rational numbers. So yeah, this is easy, right? This is easy. How you will do this? I hope I done this already, but let's do this again. So how you will do this? For any rational number, phi mapping the homomorphism fixes all rational numbers, right? See, the phi of 1 should be 1. That means phi of n should be n for all n belongs to natural number, right? Now for any x belongs to q, you can write x is the form of m by n. Okay. Similarly, phi of minus n you can write. Yeah, minus n, how you can write? Yeah, you can write phi of minus 1 as phi of minus 1 plus so on, so on, so on, so on, plus minus 1 is equals to phi minus 1, phi minus 1, phi minus 1, but which is okay, n times phi of minus 1 basically, right? But phi of 1 is 1, so phi, what is phi of minus 1 basically? It should be minus. Okay, phi of 1 is 1 basically, so phi of, what is phi of 1 minus 1 is equals to phi 1. Why this is phi minus 1? What is this? This is phi 0, which is 0. So that means phi 1 is equals to minus of phi minus 1. So this implies phi of 1 is equals to minus 1 is equals to phi of minus 1, right? So yeah, so is equals to minus n, right? Okay, so now x is equals to m by n, so you can write m is equals to nx, right? So phi of what happened? Phi of m is equals to m, which should be same as nx. So this implies phi of m phi x, so phi n. Okay, so what we can do is this, right? Why the screen is freezing? I don't know. Phi m is equals to phi n. Phi m equals to m equals to nx. Okay. So what is this? Phi m is equals to m equals to nx, right? Phi n phi n dot phi x. But phi m is m, phi n is n. So phi x is equals to m by n. So phi of m by n is equals to m by n for all. Okay, m by n belongs to q. Yeah, so we are done. That means phi r is equals to r for all r belongs to q. We proved this, right? So this is done. So this is true statement. So this is true. What is the next part? K comma f are field extension of q root 2 and phi mapping q to f is a field homomorphism. Then phi alpha is alpha for every uh, uh, alpha belongs to root 2. Okay. So what is this? If k comma f are field extension of q root 2, if k comma f are field extension of q root 2, then what? And phi mapping k to f is any field homomorphism. Is, then it is saying that phi of r is equals to r for all r belongs to q root 2. But it is not true, right? False. Why? Why it is not true? Take root 2 to minus root 2, right? This is the question, I guess. Yeah, phi alpha equals to 4. Yeah, this is not, obviously not true. False. Send. This is the justification. Root 2 minus root 2. Yeah, this is the justification. Third one, K is a field extension of Q, then K contained in C. Yeah, K is a field extension of Q, then K contained in C. No, it is not true, right? There may be some transcendental extension. K is a field extension of Q. K contained in C. No, not true, right? K is a field extension of Q. Then K contained in, no, it is not true, right? It is not true. What is the third? C. If K is field extension of Q, then K contained in C. Let's check the field extension. K is equals to Q. Okay. K is equals to function field of C x1 x2. Yeah, Q x1 x2 basically. Write it again. A is equals to function field of Qx, then is field extension. Oh, sorry. Write this as this bracket. Is field extension with Qx does not contain in C. Yeah, so C is false. So what is the next part? If K is a subfield of C, then Q contained in K. If K is a subfield of C, then Q contained in K. So how you will prove this? K is a subfield of C, then Q contained in K. K is a subfield of C, then Q contained in K. Yeah, this I proved the last time, right? It is true. How you will prove this? K is a subfield of C, then Q contained in K. So C, I will prove this. K is a subfield of C, then Q contained in K. So that L is subfield of C. So now that means Z sits inside L. Okay. This implies Q sits inside L. That means okay, we are done. So what is next problem? If K be a field such that only irreducible polynomial in Kx are the polynomial of degree 1, Q denote the field of rational number, R denote the field of real number. Okay. Okay. So this is the next question. question field such that only irreducible polynomials are polynomials of degree 1. Okay, so what? So what? First is that K can be finite field. Can K be finite field? Okay. How you can say that this K is finite field? This cannot be finite, right? How you will justify this? This cannot be finite field. Give me a justification for this. This cannot be finite field. So this is false. K cannot be finite field. You have to show me that there must be infinite element if only reducible polynomials are of degree 1. So how you will do this? See how you will do such kind of thing. This polynomials root you know all different. Okay. Okay. K field. Let characteristic of K equals to P. Right. Then what? Then what? Characteristic of K is P. Finite field, then characteristic must be 0. Characteristic 0 fields are infinite field, basically they contain. So yeah, characteristic Kp. So what? If you choose this polynomial, fx is equals to x to the power n minus 1. Let's choose this polynomial. Then what is f dash x? N x to the power n minus 1, right? If p does not divide n, then all roots of fx are distinct. So right, as n tend to infinity, this will give infinitely many element in field. So K can not be finite, right? So this option is false, right? So K cannot be finite field. K has no finite extension of degree at least 2. K have no finite extension, right? Yeah, this is correct, right? How you will prove this? This is easy, right? Since K is algebraically means every polynomial, how degree 2 extension will come arise? Degree 2 extension will come arise by adjoining a root of degree 2 polynomial. But there is no polynomial of degree 2 irreducible, right? Degree 2 polynomial is reducible. Every polynomial can be written as a linear factor. So B there does not exist any extension of degree 2 of T. True. There does not exist any reducible degree 2. Right. So third is there exists alpha belong to K such that alpha to the power 4 minus 3 alpha cube plus 2 alpha square plus 3 equals to 0. So whatever the polynomial 3 alpha 3 alpha cube 2 alpha square plus 3. See, there exists alpha belongs to K such that alpha to the power 4 minus 3 alpha cube plus 2 alpha square plus 3 is equals to 0. Yeah, there exists because true. Justification is that fx is equals to x to the power 4 minus 3x square plus what I write 3x square plus 2x cube plus 3 belongs to kx. So every since every root of fx is in k, this implies such choice of alpha exists. So this is true. So what is the next option? What is the next? If k contains q, then k contains in R. Is this true? If k contains q, then k contained in R. This is obviously not true. C contains q, but C does not contain R. Right? Contains q, then k contained in R. This is obviously what false. What is the example? K equals to C. C contains q. C does not contain R. Yeah, this is the second problem. F23 denote the field containing 23 elements which call correct statement. What is true, what is false? From two of them, only one can true, right? Either one exactly one root or exactly can two root, or can no root be also possible? So what is true? And this should be obvious. How you will encounter such kind of thing? This is easy, right? So see, over any finite field, a to the power p is equals to a, right? Fp. Oh, sorry, over fp. A to the power p is equals to a for all a belongs to fp. This implies 17 to the power 23 equals to 17 is only solution. So first one is true, second one is false. What is next option? What is next option? Give me a second. Okay, so what is next option? X square equals to 2 has exactly one root in F22, 23, and x square equals to 2 has exactly two roots in F23. X square equals to 2. Okay, so tell me. X square equals to 2. How will do? See, x square equals to 2 has exactly one root in F23. And the last one is that x square is equals to 2 has exactly 2 root F23, right? So this is the thing. There is some participant, I guess. Yusuf Govani, are you student of this course?
No, I'm not student. I'm just watching because I got the link from the from the email.
Okay.
If it's okay to watch.
Yeah, sure.
Thank you.
Okay. X square equals to 2 has exactly one root in F23. So yeah. So okay, what we did in first part, this is the question. So F23 denote the field of containing 23 element, F23 basically Z mod 23Z. So the option is that x to the power 23 equals to 17 has exactly one root in F23, and second is x to the power 23 equals to 17 has exactly two root in F23. So we, by the fact that a to the power p equals to a for all a belongs to fp, so that means 7 to the power 23 equals to 17 is the only solution of this equation. So exactly one root in F23. So a is true and b is false. Now the C option is x square equals to 2 has exactly one root in F23 and exactly two root in F23. So what x square equals to 2 means? What x square equals to 2 means what in F23? X square equals to 2 means x square equals to 23 multiple of z plus 2, this form, right? X square should be of this form. So what are the choices? One choice is 5, right? 5 square is equals to 25 is equals to 23 plus 2. One choice is 5. At least there is one rule. What are other choices? What are other choices? What are other choices? How you take? Is there any other choice? One at least exists, but is there two? Okay. 23z plus 2. Okay. 2 square 4, 3 square is 9, 4 square 16, 5 square 25, 6 square 36, which is not true. 7 square 49, which is also not true. 8 square 64, which is also not true. 9 square, okay, is not true. 10 100 is also not true. So what is other choice? Okay, there should be one other choice also. Up to 10 there is no choice, but what is the other choice? Can you see something? What is the other square such that this is of the form x square equals to 23z plus 2? What is the choice for x? Okay, one is to do this by calculation, but there should be some short trick also, right? 19 square is what? 361. What is v divided by 23? Okay, there is two choices of this, so we have to calculate. Up to 10 there is no other choice. 11 121. Okay, So there are at least one choice there exists. 5 is the one choice. What are the other choices? Is there exist another other choice? We need to find that, right? So up to 10 there is no other choices. From 11 onwards we have to check what is the okay. Okay, so okay, let's play this equality. If we can do something from 23 dot uh, 23p plus 2, right? So x square minus 2 should be multiple of 23p. Some p belongs to z, right? So this form. So what are the choices of x? We need to find this, right? So from here what we can do, x square minus 2 is 23p. So 23 divides x square minus 2 in that case. So what are such choices of x basically? What we can do from here? So what are such choices of x? Do we need to explicitly do computation? This number is too big. Give me a second. Can we do it some other way? Let me check. There should be some nice way to do this. Okay, one is its inverse will be choice. Okay, its inverse will be other choice. So what is this? 5 inverse in f23 19. Okay, 5 7. Sorry, sorry for this, but yeah, 19 into 5 is this. Okay, so yeah, so other choice is what? One choice is 5, but what is the other choice? There should be some other choice also. Maybe its inverse is the right choice, but I don't know how to. What is inverse of 5 in this one? Okay, so there are exactly two choices. One is 5, one is 5 inverse. Okay, okay. What is this? 5 inverse square is equals to 5 square. I don't know. I don't know. This is not working. So there are two choices. One is 5, other one just calculate what is the other choice. But there are two choices. You can compute just a square. X square has actually one root. This is false and this is true. Okay. What is the next question? Choose all correct statement. Yeah, this is the right. There is a field of order 1 to 8. Just find prime factorization of 1 to 8, 3125, 245, 2400. So if there is any other number, this should be the, I did this problem in last lecture. Right? So choose all correct statement. Let's do this again. First is this. There is a field of order 1 to 8. How you will do this? 1 to 8. What is prime factorization of 1 to 8? 2 4s are 12, 2 sorry, 2 6 are 12, 2 4s are 8, 64. What is how you can do 1 to 4, 2 6 are 12, 2 4s are 128 है, 2 3 are 6, 2 2s are 4, 16, 8, 2. So see, this is 2 to the power n form ka. So this is that 2. True. So what is B? There is a field of order 3125. So what is 3125? This is not working. How you can write 3125? 5, 5 6 are 30, 5 2s are 10, 5 5s are 25, 5 1s are 5, 5 2s are 10, 5 5s are 25, 5 2s are 10, 5 5s are 25, 5 5s are 25. So this is right. 1 2 3 4 5, 5 to the power 5. This is 5 to the power 5. So yeah, this is also true. So what is next one? Why this is happening? See, what is the third part? There is a field of order 245. There is a field of order 245. This is not true. So how you will do this? 245, do its prime factorization. You can do 5 4s are 20, 5 4s are 20, 5 9s are 45. So yeah, so this is 5.7 square. So this implies there does not exist any such field. And the last one is there is a field of order 2400. So yeah, what is the factorization of 2400? 2 1 are 2, 2 2 are 4, 2 6 are 12, 2 3 are 6, 2 1 are 2, 2 5 are 10, 75. Now it is not right. So this is false. This is false. Why? This is of the form 2 to the power dot 5 to the power k to the power r. So yeah, this is not true. And this should be some single power if it is there exists of some field of p to the power n. So this is not true. So what is the next question? First do this one. Choose all correct statement. The first statement is degree of a splitting field of x to the power 5 minus 1 over q is 4. So this is true, right? I already covered all the theory of this type, x to the power n minus 1. So this is equals to 5 is equals to 4. So this is true. So the second one is degree of splitting field of x to the power 7 minus 1 over q is 7. Of splitting field of x to the power 7 minus 1 over q is 7. False. Why? 5 7 equals to 6. So this is false. What is next? Degree of splitting field of x cube minus 2 over q is 3. Third, degree of splitting field of x cube minus 2 over q is 3. So what is this? Is false, right? Why? What are the root of this? Its roots are 2 to the power 1 by 3, omega 2 to the power 1 by 3, and omega squared 2 to the power 1 by 3. So what is omega? Minus 1 plus minus iota root 3 by 2, right? So we need to splitting field is q adjoined with iota comma 2 to the power 1 by 3. It see. What is the splitting field? Omega is equals to minus 1 plus minus iota root minus 3 by 2 iota root minus x square. तो splitting field ये नहीं होगा, इरेज करो इसको. Iota root 3 comma 2 to the power 1 by 3. So iota root 3 is root of what? X square plus 3, right? And okay, so what is this? Q say q adjoint 2 to the power 1 by 3, say q adjoint iota root 3, right? यहाँ से q iota root 3 comma 2 to the power 1 by 3. This is 2 degree extension, 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 this is 4 degree extension. So yeah, this is not true, false. Degree of a splitting field of x to the power 4 plus 1 over q is 4. This thing I already done. This is true. In last session I done. This is irreducible polynomial. X to the power 4 plus 1 over. Okay. So D the degree of splitting field of x to the power 4 plus 1 over q is 4, right? Ah, right. So x to the power 4 plus 1, how you can write? X to the power 4 plus 1. What is this? X to the power 4 plus 1 is what? X square plus iota x square minus iota, right? Okay, let's erase this. This is like not working. What are its roots? See, roots of x to the power 4 plus 1 equals to 0. What are its root? X to the power 4 is equals to minus 1. So what are the roots? That means x is equals to minus 1 and all other fourth primitive root of it. 1, y1 is root 1 minus 1 iota minus iota, right? X to the power 4 is equals to minus 1 means x to the power 4 is equals to minus 1 means what is the root? Iota to the power 4 is equals to minus iota to the power 4, right? Iota square is minus 1, iota to the power 4 is 1. So x to the power 4 should be minus 1. What is that? No, x to the power 4 is equals to minus 1 means cos pi is minus 1. Cos pi is minus 1 and cos pi plus I sin pi, right? Power e to the power I pi, right? Okay, so you can compute all those values. I had done this in one of sessions. E to the power I pi, which is minus 1. So this is to the power I pi by 4 basically, which is cos pi by 4 plus I sin pi by 4. Cos pi by 4 is 1 by root 2 plus I sin pi by 4. I sin pi by 4, 1 by root 2. Yeah. So this is the root 1 by root 2. So let's name this as a alpha. So what are alpha, comma minus alpha, comma iota alpha, comma minus iota alpha? All these are roots. Alpha, all these are roots. So we need to add only this root, right? We only need to add root 2. So splitting field of x to the power 4 plus 1 is q iota comma root 2. So q say q root 2, say q iota, say q iota comma root 2. तो ये 2 डिग्री, ये भी 2 डिग्री, ये भी 2 डिग्री, ये भी 2 डिग्री, ये 4 डिग्री का एक्शन. So this is done. Yeah, this is done. So yeah, so with this I will stop here. Okay. So yeah, since the video started, I forgot to start recording initially, so the video is started late. So that's why I increased the session by 40 minutes, and so that the recording will have enough. Recording will about 1 hour. Yeah, one plus half an hour, right? So yeah. So with this, I will stop this session. So I hope you enjoyed these sessions with me. If you have any doubt and you are interested in these stuff and you want to discuss with someone, and you can mail me. You have my mail ID, and we can discuss there. So with this, I will stop, and bye bye to you from this course. Thank you.